Generative models are a fascinating area of artificial intelligence and machine learning, enabling us to create and generate new data samples that closely resemble our training data. Imagine being able to synthesize realistic images, text, or even music that feels truly authentic. Isn't that incredible? In this lesson, we're going to dive into the world of generative models, exploring what they are, how they work, and coding a few examples in Python using PyTorch. So, get ready to embark on this exciting journey of creativity and data. Now, let's implement a simple Generative Adversarial Network, or GAN, using PyTorch. We're going to start by importing the necessary libraries, including PyTorch and TorchVision, which are, really handy for building neural networks and managing datasets. So the GAN itself has two main parts, the generator and the discriminator. Both of these are defined as classes that inherit from nn.module. The generator's job is to create new data samples from random noise. It takes a 100-dimensional input and passes it through several layers with ReLU activation functions. And guess what? It outputs images reshaped to 28 by 28 pixels using the TON activation function to make sure the values stay in the range of -1, 1. Pretty neat, right? Now, on the flip side, we've got the discriminator. Its task is to differentiate between real and fake images. It takes a 784-dimensional input, processes that through a series of layers with Lie-ReLU activation, and then spits out a single probability score, indicating whether the input is real or fake. Next up, let's define our hyperparameters, including batch size, learning rate, and the number of training epochs. Then we'll prepare the MNIST dataset, applying normalization and loading it into a data loader for mini-batching. After that, we initialize our generator and discriminator networks, set the binary cross-entropy loss function, and get optimizers ready for both networks. Finally, we set up a training loop. For each epoch, we train the discriminator on real and fake samples, and then we train the generator to create better fakes. This adversarial process goes on iteratively, allowing both networks to improve through competition. As each epoch wraps up, we print out the discriminator and generator loss. This gives us some insight into how things are progressing through the training process. The figure titled Applications of Generative Models features a vertical bar chart that illustrates how much focus is given to various application areas. On the y-axis, we measure as percentage of discussion, while the x-axis categorizes 5 main areas: image generation, text synthesis, data augmentation, style transfer, and deepfakes. Each bar is topped with a numeric label indicating its exact percentage. Image generation sits at 25%. Text synthesis leads with 30%. Data augmentation at 20%. Style transfer at 15%. And deepfakes trails at 10%. If we look closely at these figures, a clear hierarchy emerges. The largest slice of discussion, 30%, goes to text synthesis, followed by image generation at 25%. Then we have data augmentation at 20%, with style transfer at 15%, and finally, deepfakes down at 10%. A key takeaway from this chart is that more than half of our conversation, specifically 55%, is centered around text synthesis and image generation, highlighting a focus on these two areas. So, as you approach this material, prioritize diving deep into methods and examples relevant to text and image generation first. But don't forget, data augmentation, style transfer, and deepfakes are also important, just covered with a bit less intensity. Now, let's implement the Variational Autoencoder, or VAE model. We begin by defining the encoder class, which transforms an input of 784 dimensions into two distributions that represent the mean and the log variance. This design is super important for our variational sampling process. Using a fully connected layer, it reduces the dimensionality and applies the ReLU activation function, which helps ensure non-linearity. Such a key aspect, right? Next, we have the decoder class, and this one takes our latent representation and attempts to reconstruct the original input by reversing the encoding process. This involves another set of fully connected layers, and it applies the sigmoid activation function to output values between 0 and 1. Now, let's look at the main VAE class that integrates both the encoder and decoder. It performs this nifty reparameterization trick, which allows for gradient-based optimization of the latent space during training. This basically involves sampling from a distribution defined by the mean and log variance. Finally, we need a loss function that, well, combines binary cross-entropy with Kullback-Leibler divergence to quantify the difference between the learned distribution and the true distribution. This gives us a measure of how well the VAE reconstructs its inputs while also maintaining a structured latent space. And that structured space, it's not just for show. It enables us to effectively generate new samples while retaining those important characteristics of our training data. In practice, training a VAE would be quite similar to what we did with the GAN. You'd load your dataset and implement a training loop that optimizes the VAE's loss function. Throughout the iterations, the VAE learns to create new data points resembling our training data while allowing for smooth transitions across the latent space. Now, let's take a break for a moment. How cool is it that we can create entirely new images from scratch? Generative models have opened an exciting avenue for creativity and automation in various fields, such as art, music, and even game design. Imagine using AI to generate unique character designs, bustling cityscapes, or intricate patterns based on simple inputs. Generative models also pave the way for advancements in data augmentation, allowing us to artificially expand our datasets by creating realistic variations of existing data. This can be particularly useful in scenarios where collecting real data is time-consuming or expensive. Through techniques like augmentation, we can reduce overfitting and improve the predictive performance of our models. That's an essential aspect of building robust AI systems. Now, let's implement the following code to generate text using the pre-trained GP2 model. First, we begin by importing the necessary classes from the Transformers library, specifically GP2LM head model and GP2 tokenizer. After that, we'll load the pre-trained model and tokenizer by specifying the model name, which is set as GP2. The tokenizer will take care of converting our textual prompt into a format that the model can understand, transforming it into tensors suitable for input. All right? Next, we define a prompt that serves as the starting point for our text generation, something like, "Once upon a time in a land far away." We then pass this prompt through the tokenizer, encoding it into the required tensor format. The critical point here is utilizing the generate function, where we specify the maximum length for the output and how many sequences we want to return. After invoking this function, we get our generated outputs, but hang on, these are still in tensor format. To make the generated text readable, we need to decode the first output tensor back into a human-readable format using the tokenizer. Finally, we print the resulting text, which showcases the coherent continuation of the narrative initiated by our prompt. This way, we can observe how GP2 constructs sentences that align beautifully with the context provided. In satisfaction. Generative models hold transformative potential in various industries, and the more we explore them, the more fascinating applications we uncover. They can revolutionize the way we think about data, decision-making, and creativity. It's pretty incredible, right? As you've seen from the code examples, implementing these models is accessible, and honestly, they can yield some really impressive results. So let's wrap this up. In conclusion, generative models are not just about creating new samples. They encapsulate a broader vision of understanding and recreating the world around us, driven by data and patterns. Whether it's visual art, music, or even natural language, these models empower both creators and scientists alike. As technology keeps evolving, I can tell you, those who harness the power of generative modeling will surely be at the forefront of innovations that reshape our daily lives. So let's keep exploring this exciting field, unraveling new possibilities with every line of code we write.